A brief history of time interpretation. The cosmic question under the night sky. Humanity gazes at the stars, pondering, where do we come from? Does the universe have an end? What is time? These questions have haunted us since ancient times, from Greek philosophers to modern scientists, all striving to unravel the universe's mysteries. Stephen Hawking, a towering intellect confined to a wheelchair, opens a window to the cosmos in a brief history of time. With scientific language, he narrates the origin and end point of time. This book is not just a scientific masterpiece, but an adventure in human understanding. It blends complex physics with our fundamental questions about existence, guiding readers through black holes and across galaxies to confront the essence of time. Let us follow Hawking's footsteps to explore the universe's mysteries and feel the boundless potential of human wisdom. 2. The beginning of time. Does the universe have a starting point? In A Brief History of Time, Hawking boldly proposes that time began 13.8 billion years ago with a Big Bang. This Big Bang theory revolutionized our understanding of the cosmos. Picture an infinitely hot, dense singularity, containing all matter and energy, erupting in an instant to form space, time, and everything. To grasp this, recall Georges Lemaitre, a Belgian priest who, in the early 20th century, suggested the universe originated from a primeval atom. At the time, many scientists, including Einstein, dismissed it as far-fetched. But in 1929, astronomer Edwin Hubble observed through his telescope that galaxies are moving away from us, proving the universe is expanding. This discovery was a beacon, illuminating the fog of cosmic origins. The Big Bang wasn't an explosion, but a rapid expansion of space itself. Hawking uses a vivid analogy. Imagine inflating a balloon, where points on its surface move apart as it grows, with no single point as the center. The universe's expansion works similarly, with no fixed starting point. This makes complex physics tangible and relatable. But what does the beginning of time mean? Hawking suggests time may not have existed before the Big Bang, challenging our intuition of time as an ever-flowing river. He tells us this river has a source, beyond which lies the boundary of science and the starting point of philosophy. The Big Bang theory's validation owes much to modern astronomy. Beyond Hubble's redshift observations, the discovery of cosmic microwave background radiation provided direct evidence. In 1965, physicists Arno Penzias and Robert Wilson accidentally detected a uniform microwave signal permeating the universe. This afterglow of the Big Bang, at about 3 Kelvin or 270 C, confirmed its fiery origin. Their discovery earned them the 1978 Nobel Prize in Physics. To vividly understand this, imagine a fictional astronomer, Elena Soto, recording microwave signals at a Chilean radio telescope. She muses, this signal is like the universe's whisper, telling the story of its birth. Elena's metaphor reveals the poetic side of science. The Big Bang theory also sparks philosophical questions. If time has a beginning, what was before? Hawking notes this question may be unanswerable, as our scientific language cannot describe before. Ancient Greek philosopher Aristotle believed the universe was eternal, but the Big Bang theory presents a finite cosmos. This shift makes us reflect on humanity's smallness and greatness, mere specks in the universe, yet capable of probing its origins through science. Lemaitre's theory wasn't mere speculation, but rooted in mathematical models. In the 1920s, using Einstein's general relativity equations, he deduced the universe began expanding from a high-density state. His work laid the foundation for the Big Bang theory. Hawking expands this picture, noting the Big Bang was not just time's start but space's beginning. He introduces the no-boundary proposal, suggesting the universe may lack a distinct starting point, akin to Earth's surface finite, but without edges. This analogy reshapes our view of the universe's nature, possibly finite, yet boundless. To visualize the Big Bang's instant, imagine a fictional physicist, Alyssa Novak, likening it to a fireworks display, a dazzling burst in darkness, scattering countless particles across vast space. Alyssa writes, the Big Bang didn't happen in space, it created space itself. Her metaphor captures the grandeur and mystery of cosmic birth. The Big Bang theory also raises another question: how did the universe's initial conditions form? Hawking explores quantum mechanics' role in the early universe, suggesting tiny quantum fluctuations shaped galaxy formation. These fluctuations are like ripples on a calm lake, stirred by a breeze, ultimately sculpting the universe's structure. This view links the microscopic and cosmic, showcasing science's remarkable unity. 3. The mystery of space. If time has a beginning, what is space? In A Brief History of Time, Hawking uses general relativity to depict space's essence. Einstein's general relativity posits that space and time are not separate backdrops, but an interwoven spacetime, warped by matter and energy. Imagine a taut bedsheet with a bowling ball placed on it, creating a dip and gravity well. Planets and stars similarly warp spacetime, guiding objects along curved paths. This insight came from Einstein's 1915 publication of General Relativity amid debates over gravity's nature. Newton's gravity theory explained planetary motion, but not why gravity acts instantly across space. Einstein proved gravity results from spacetime's curvature, explaining planetary orbits and predicting light bending in gravitational fields. In 1919, British astronomer Arthur Eddington confirmed this during a solar eclipse, observing starlight bending near the sun. This observation stunned the world and made Einstein famous overnight. Hawking extends this idea, exploring space's dimensions. We live in three-dimensional space, but Hawking suggests the universe may have more dimensions, curled up to scales too small to see. Imagine a fictional physicist, Isaac Brandt, studying string theory, comparing higher dimensions to a rope, one-dimensional from afar, but up close, composed of tiny loops representing extra dimensions. This analogy helps us grasp that the universe's true nature may exceed our perception. Higher dimensions aren't mere fantasy. Hawking notes string theory suggests 10 or 11 dimensions, compacted to the Planck scale about 1035 meters. To make this concrete, imagine a Chinese physicist, Qi-Ming Liang, studying superstring theory in Shanghai. Likening the universe to a book, we see three-dimensional pages, but extra dimensions are like tiny creases between them, shaping the whole. Liang's metaphor reveals the wonder of higher dimensions. General relativity also predicts time dilation, strong gravitational fields, time slows. Hawking describes a thought experiment: an astronaut near a black hole experiences slower time than on Earth. In 1971, physicists Joseph Haffel and Richard Keating tested this, flying atomic clocks across the Atlantic, finding they lagged by fractions of a second. This confirmed Einstein's theory and revealed spacetime's dynamic nature. General relativity impacts modern technology like GPS. Due to Earth's gravity, satellite clocks run slightly faster than ground clocks. Without relativity corrections, GPS accuracy would falter. Imagine a Chinese engineer, Chen Zhao, developing navigation systems, noting that ignoring relativity causes cumulative errors, rendering navigation useless. Zhao remarks, Einstein's theory is not just a cosmic compass, but a cornerstone of daily life. This shows how abstract physics shapes reality. General relativity also inspires sci-fi, like Interstellar, where time dilation near a black hole causes years to pass on Earth while minutes elapse for astronauts. This stems directly from Einstein's theory. Hawking notes that general relativity redefines space, not a static stage, but a dynamic arena, performing the cosmic drama alongside time. 4. The shadow of black holes. Black holes are perhaps the most captivating topic in A Brief History of Time. Hawking describes them as spacetime abysses, with gravity so intense that even light cannot escape. Black holes form from dying massive stars, collapsing under their own gravity into a singularity of infinite density, cloaked by an event horizon. Hawking's work goes beyond describing black holes. His 1974 Hawking radiation theory challenged the idea that black holes swallow everything. Using quantum mechanics, he showed black holes emit particles due to quantum effects, potentially evaporating over time. This discovery stunned physics, merging general relativity with quantum mechanics and opening new research frontiers. Hawking's personal story adds emotional depth. Diagnosed with ALS at 21 in 1963, given 2 years to live, he defied odds, contemplating black holes from his wheelchair. His resilience shows how science's boundaries are pushed by those who defy fate. To understand Hawking radiation, imagine a fictional astronomer, Maria Castro, explaining it with virtual particle pairs. Near a black hole, one particle is swallowed, the other escapes, forming radiation. Maria writes, "Black holes aren't eternal graves, they fade in time's river." Her metaphor captures their dynamic beauty. Black hole research sparked the information paradox debate. Hawking suggested evaporating black holes might lose information, clashing with quantum mechanics. Hypotheses like black hole complementarity and firewall theory emerged to address this. Later, Hawking proposed information might be stored on the event horizon as a holographic projection. This idea bridges physics and philosophy. To clarify the paradox, imagine a theoretical physicist, Sophia Gray, likening information in a black hole to a book. Though it seems lost, it may persist on the boundary, like a shadow on a wall. Sophia's thought highlights black holes as tests of cosmic rules. Black holes influence culture and imagination. Hawking's radiation theory transformed them from mysterious devourers to dynamic systems, inspiring sci-fi-like frequency, where black holes enable time travel. Hawking embraced pop culture, even guest starring in Star Trek, playfully playing chess with Einstein. This crossover shows black holes as symbols of human curiosity. Imagine an Argentine sci-fi writer, Carlos Mendes, inspired by Hawking, writing, "Black holes are cosmic gatekeepers, hiding time and space's secrets." His work makes black holes accessible to readers. Scientifically, black holes advanced astronomy. In 2019, the Event Horizon Telescope captured the first black hole image, a blurry orange ring, confirming Hawking and Einstein's predictions. Though Hawking didn't witness it, his theories paved the way. The expanding universe. The universe not only began, but continues to expand. Hawking details this in A Brief History of Time, exploring the force behind it, dark energy. In 1929, Edwin Hubble's telescope observations showed galaxies receding, confirming cosmic expansion. Yet, why this expansion accelerates puzzled scientists. In 1998, two teams studying distant supernova found they receded faster than expected, revealing dark energy's existence. This mysterious force, about 68% of the universe's energy, acts like anti-gravity, driving accelerated expansion. Picture an inflating balloon, its surface expanding faster over time. Dark energy is the unseen force. Hawking highlights astronomer Vera Rubin's 170 seconds discovery that galaxies rotate faster than expected, suggesting invisible dark matter. Dark matter and dark energy shape the universe's structure and fate. Dark matter, about 27% of the universe's mass, doesn't emit or absorb light but influences gravity and galaxy formation. Rubin's observations provided key evidence. To vividly grasp dark matter, imagine a fictional astronomer, Carl Sagan, in Chile's Atacama Desert, tracking galaxy motions, noting, "The universe is an invisible canvas. We see only its outlines." Dark energy's discovery was even more enigmatic. The 1998 supernova studies, led by Brian Schmidt and Adam Rees, showed accelerating expansion, earning them the 2011 Nobel Prize. Hawking suggests dark energy may dictate the universe's fate, endless expansion to a heat death of cold uniformity or another unknown end. To clarify dark energy, imagine a Chinese astronomer, Ruoxi Lin, at Yunnan's Lijiang Observatory, likening it to an invisible conductor speeding up the universe's symphony. Lin's metaphor captures the dynamic beauty of expansion. Dark matter and energy remain cosmic mysteries. Dark matter, though shaping galaxies, evades direct detection. At CERN's Large Hadron Collider, scientists like a fictional Egyptian physicist, Amina Hassan, seek dark matter particles, noting, it's the universe's invisible sculptor, shaping galaxies yet never seen. Dark energy's nature is murkier. Hawking suggests it might be a cosmological constant or a dynamic field. The DESI project in the 2020s, mapping galaxy distributions, hints dark energy may evolve, potentially rewriting cosmic fate. Hawking's insights guide these studies like a beacon. The arrow of time. Why does time always move forward? Hawking introduces the arrow of time, tied to the second law of thermodynamics, which states entropy disorder always increases. A broken cup doesn't reassemble. Hot coffee cools time's direction is clear. Hawking identifies three arrows: thermodynamic entropies rise, psychological our perception of time, and cosmological universe's expansion. These likely align because expansion drives entropy, and our memory relies on this process. Imagine a philosopher, Sophie 11, recalling a childhood experiment: a drop of ink spreads in water. Never reforming, no, time is like this ink, flowing toward chaos. Her reflection blends science's rigor with philosophy's poetry. Hawking explores time travel via general relativity's wormholes, theoretical tunnels linking spacetime points. Yet, paradoxes like the grandfather paradox pose challenges. What if you prevent your own birth? With humor, Hawking writes, I held a time travel party, but no one showed up. This quip reflects his blend of rigor and wit. To explain entropy, imagine a British physicist, James Carter, likening it to scattered building blocks that never reassemble themselves, illustrating time's direction. Time's arrow shapes memory and existence. Hawking notes our psychological arrow aligns with thermodynamic, as memory formation depends on entropy's rise. Neuroscientist Margaret James found memory storage consumes energy, aligning with thermodynamics, noting, our memories are shadows of time's arrow, recording the universe's passage. This sparks questions about free will. If time's arrow dictates irreversibility, are our choices free? Hawking offers no final answer, but notes science brings us closer to truth. Imagine a Chinese philosopher, Ruohan Li, writing, time's arrow makes us narrators of a story we cannot redirect. Her thought merges science and philosophy, urging us to rethink existence. Hawking suggests time's arrow ties to the universe's low-entropy initial state at the Big Bang, setting its flow. Imagine a Chinese physicist, Yuchen Zhang, studying cosmic background radiation, noting its uniformity hints at low entropy, writing, time's arrow is a river, its course set by the universe's start. Her metaphor ties time to cosmic origins. The quantum universe's frontier. Hawking delves beyond the macroscopic, exploring quantum mechanics' role in a brief history of time. Quantum mechanics governs the subatomic world's oddities, like wave-particle duality and uncertainty. Hawking suggests it was crucial in the universe's earliest moments. He introduces imaginary time, where near the Big Bang's singularity, time may bend like space, not linear. This stems from his no boundary proposal with James Hartle, suggesting the universe is like a smooth sphere, with no start or end. Hawking likens it to Earth's surface, walk forever, yet find no beginning. Imagine a fictional physicist, Emma Frost, describing imaginary time as air inside a balloon, invisible, yet supporting its structure. Her analogy captures the quantum universe's abstract beauty. Quantum mechanics explains cosmic structure formation. Hawking notes quantum fluctuations in the early universe seeded galaxies and clusters. 1980 seconds observations, like the COBE satellite's detection of tiny temperature variations in cosmic background radiation, confirmed these as galaxy origins. Imagine a German astronomer, Lucas Weiss, likening fluctuations to ripples on a beach, forming grand dunes, showing cosmic structures' microscopic roots. Quantum mechanics also sparks multiverse theories. Hawking suggests quantum mechanics allows the universe to branch into parallel states. Though unproven, this inspires debate. Imagine a Chinese physicist, Rulanshan, writing, "If our universe is a tree, the multiverse is a forest, each tree with its own tale." Her metaphor evokes cosmic possibilities. The quantum universe raises philosophical questions. Hawking's no-boundary proposal, suggesting no distinct start or end, echoes Buddhist ideas of no beginning, no end. Imagine a Japanese philosopher, Mako Ando, writing, "The universe is a boundless circle. Quest for a start loops endlessly." Her analogy blends quantum physics with philosophy. Quantum mechanics challenges reality's nature. Hawking notes quantum superposition means the universe may exist in multiple states until observed, aligning with the many worlds interpretation. Imagine a British philosopher, Alan Black, likening the universe to an unwritten novel, each page holding countless endings. His thought ties quantum mechanics to our understanding of reality. 8. Humanity's Starry Sky, A Brief History of Time, is more than a scientific work. It's an epic of human curiosity. Hawking shows the universe's mysteries are within reach through science. He writes, "However brief our lives, understanding the universe lets us touch eternity." His words inspire countless minds. From Galileo's stargazing to Hubble's galaxy observations, each exploration expands our knowledge. Hawking's wheelchair-bound life embodies this, probing the infinite with a finite existence. Imagine a Polish astronomer, Natalia Cowell, inspired by Hawking while studying exoplanet, writing, "Science is not just equations and data, but a love for the unknown." Her story underscores science's generational effort. Today, the James Webb Space Telescope reveals distant galaxies, and quantum computing may unlock deeper cosmic secrets. Hawking's questions, "What is the universe's fate? Will time end?" await answers. Future generations may find them. Imagine a young Chinese scientist, Tianyu Zhou, studying dark energy, likening science to a boat sailing in cosmic ocean toward the unknown. His metaphor captures science's adventurous spirit. Gazing at the stars, we're all part of the cosmic story. Hawking's A Brief History of Time reminds us, no matter how vast the universe, human wisdom and curiosity weave time and space into eternal brilliance in our minds.